Hello, my name is Timur Babakol, and I'll be presenting our work at SUNY Binghamton on Calm Energy Accounting in Java. Energy accounting is a division of global energy over a set of components. The components are an abstraction that we can choose freely, such as hardware accounting, a breakdown by physical component, allowing low-level studies of the system. We can also do OS accounting, a breakdown by executing components, such as processes or threads. Our work focuses on application energy accounting, a breakdown by logical units such as methods, classes, or packages. Application level energy accounting is a fundamental part of green software engineering. An implementation of such an accounting system opens up avenues for energy-aware design, energy testing and debugging, and energy optimization. Today, we're going to be presenting an implementation of such a system called Chappie. It's a novel sampling-based runtime system that draws information from multiple layers of the computing stack and composes it to produce an energy footprint. Such a footprint is shown at the method level here. So for this particular one, we're showing the normalized energy and normalized runtime for all of the methods across some program, being able to show the comparison of energy behavior as well as the power behavior. Chappie has three crucial features. First, it performs total accounting. All methods are accounted for. Second, it's concurrency aware, as in line with modern applications. Third, it maintains calmness, so the profiler is not going to disturb the application's original behavior. In order to build some motivation for why these three features are so important, let's start with the naive approach to accounting, which is instrumenting methods on exit and entry. Take the method foo, for example. When the method starts and ends, we read the amount of energy and compute the difference as the accounted value. This is not actually going to produce a valid result. The first issue is that is totality. We want all methods to be accounted so we can get a complete study of the application. So we're going to need to instrument every single one of these methods, and this is not going to scale well. You can even see we have some numbers here demonstrating how that actually performs, that even at 5% instrumentation, the slowdown is too significant on the application. Second is concurrency. Let's say, for example, like in the figure here, we have two co-running instances of foo. When the first instance of foo exits, when the energy sample it takes is taken in the same time as the second instance of foo. As a result, we don't actually know how to fairly distribute the energy between these two methods, and we'll end up over-accounting, giving too much to both of them. Finally, we need to address calmness. Profiling is going to impact the application, and usually that's going to be checked by the overhead, checking the runtime change. But in our case, since we're doing energy accounting, we also need to observe changes in the power state, which can be reflected in changes in the CPU frequencies. And that's going to end up impacting both execution time and the total energy, as shown here for Aurora, where at very small sampling periods where many data samples are taken, the power behavior goes way up and there's even a speed up in the runtime. So we really need to make sure that we're maintaining this power behavior while sampling so that we have the same runtime as when we're not sampling. Now I'm going to describe how Chappie actually does a computation of accounting. So at every time slice, we sample the energy by energy domain from the hardware. Then from the operating system, we figure out the number of active threads on each of the energy domains. Finally, we allocate an equal slice by domain for the methods being executed by each thread, resulting in the final energy footprint for each time slice. In order to maintain calmness, we have to make sure that the application is not significantly altered in three ways: the execution time, the energy phase behavior, and the load balancing behavior. We have an example for this from the energy phase behavior in this graphic. As you can see in the original run, at the first time epoch, the program is operating at 1 gigahertz, as 2 CPUs, while in the accounting run, it's operating at 2 gigahertz. So these are the kind of behaviors that we need to make sure that are not being changed in the profiled run. Chappie runs in its own thread, co-running with the application. Energy data is collected from the RAPL system using the JRAPL framework. The time correspondence is set as a 5% difference between the profiled and the original run. And the temporal and spatial correspondences are determined through the computation of a Pearson's correlation over our CPU frequency traces. with a lower threshold set at 0.95. All experiments are conducted on a machine with 40 cores and 64 gigabytes of RAM, and the evaluation is done over the latest version of the DaCapo benchmark suite. So now I'm going to present some data of the correspondences. So this first one is going to be for H2. This is the time correspondence. So it's the % change in the application's runtime. What's very strange here is that there's actually a speed up for these very low sampling periods. So the 1 millisecond and 2 millisecond sampling periods. This is counterintuitive to what you'd expect from profilers where you're actually looking to mitigate a slowdown. What actually could be happening here is that the profiling the application has actually kicked the CPUs into higher frequencies, which have caused the speed up. Now we're going to move on to the temporal correspondence, which is going to be the correlation of the energy phase behavior between the unprofiled and profiled runs. We can actually see that this data is pretty consistent with some of the intuition that we built looking at the time correspondence. At the 1 and 2 millisecond sampling periods, the correlations are quite poor, and it doesn't improve until about 32 milliseconds, where it stabilizes at our target of 0.95. Now finally, the spatial correspondence, which is going to be the correlation of the load balancing behaviors. As you can see in this case, the spatial correspondence is really poor until 32 milliseconds. This is a really pronounced change in the disturbance compared to the previous two metrics, indicating the importance of looking at this problem from multiple axes. So as 32 is within the target of calmness for all of our values, we're going to pick it as H2 sampling rate to produce footprints. In order for us to have a better understanding of the impact of the sampling rate, we're actually going to look at some evaluated frequency data. I'm going to start with the temporal reference data, which is going to be the temporal distribution as collected from no sampling. The x-axis is the sampling epoch, while the y-axis is the percentage of cores operating at a given frequency range. When we're going to be computing our correlations, we're going to be looking to see that these frequency groups are similar for each epoch between the two runs. Looking at this plot, the behavior is pretty consistent overall, operating in the 1 to 1.5 gigahertz range. And there's a little burst of activity at the end. So this kind of trend is what we're going to be hoping to see in profiled runs that are calm. So now that we have a visualization of the unprofiled data, here's their selected rate of 32 milliseconds. This is pretty similar to the reference run, which is reflected by the fact that there's a 0.95 correlation. So that's great for us. Now let's take a look at the disturbed case. This is the 1 millisecond case. We expect it to be disturbed, but we can see that the majority of the work are in completely different frequency ranges compared to the reference data, up in the 2 gigahertz ranges. And in addition, you actually can see that the number of sampling epochs is dramatically smaller. This is, we know this to be the case as there's a speed up for the application that we've already seen from the previous correspondence data. And so as a result, we can see the effects even here in the temporal distributions. Now we're going to move on to the spatial data. In this case, the x-axis is the number of cores operating at a given frequency, and the y-axis is the chance of that particular event occurring. This is pretty consistent with what we've seen for the temporal correspondence as well as the temporal correspondences we've seen previously. And the majority of these cores operating in that 1.5 range. Again, the 32 millisecond case is very similar, in line with our 0.95 target. And finally, the 1 millisecond case, which we can see is extremely disturbed. The behavior does not look anything similar. So everything is moved up to these higher ranges. So now we should have some confidence that our sampling methodology is going to be reflective of the application's runtime. So let's actually look at some of these method footprints now. So first is going to be the method ranking that we looked at earlier. This is for the application graphchi, which is a big data framework that solves graph algorithms. For this particular benchmark, we can see we were solving ALS matrix factorization with the majority of the energy being consumed by the method update. This makes sense because this particular implementation, primarily most of the work is done within this update body. What's important is that we can see that from the data, because the energy value is higher than the time value, this should be a high power method. Given that update is also a heavily mathematical method and does a lot of matrix math, it's probably pushing the CPU into a high power state. If we wanted to check this, this hypothesis, we could look at some of these IO-intensive methods such as load, add, chunk, and read at the bottom. Both methods that we know should be loading data from disk or IO, they seem to have the opposite behavior of seeming to have a low power state. So this is a pretty good guess in terms of our intuition. Now we're going to actually change our abstraction to context sensitivity, so we can actually look at the calling context. So here's the calling context for H2 for the method page.binary search. So what's being shown here is actually the, what's being shown here, if we consider the blue slice, is that this is a fraction of energy that was consumed by binary search when it was called by cursor.min, who itself was called by cursor.hasNext. So we can change this abstraction to see how a particular method is used by the application. Something that we know to match our intuition is that for binary search, it's called recursively by other binary search implementations. So our expectations for how this algorithm should work is met. Finally, we're going to change our abstraction to point at package and class at the package and class level. This particular data set is going to be Botic, which is an SVG rendering library. As we can see from the class ranking, the majority of the work is done by encoding an encoder and a painter, which is expected for Botic as it's primarily doing rendering transformations as its workload. If we then take our granularity and make it even coarser, we actually get the package showing the implementation that we're actually using, is actually being used in order to do this work. This is all valuable information to a developer in a large scale system, since the classes are usually going to be the abstraction unit between programming tasks. As we've shown, our presented work focuses on application level energy accounting. Traditionally, other work have been primarily OS-based approaches, but Chappie is able to prove granularity at the method level. Our methodology is distinct because we provide a total concurrent aware footprint that is also disturbance mitigated. This means Chappie has potential beneficiaries in energy management optimization systems, since you can provide fine-grained information about the logical behavior of energy. In conclusion, we presented Chappie, a novel sampling system that produces an energy footprint across multiple layers of the computing stack. It's total concurrent aware and disturbance mitigated, and has a number of customizable abstractions. Thank you very much for watching.